Hey, fellow geochemists and geochemistry enthusiasts. Welcome to Geochemist Tea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire, to shed light on the topics not fancy enough to talk about at a conference, but important to delve into. I'm your host, Sam Schur, and this week we are talking with Tom Carmichael about the importance of spatial predictor variable selection in machine learning applications, moving from data reproduction to spatial prediction, a paper by Meyer et al. In 2019. Tom Carmichael is the chief data scientist at DataRock, and while not a geochemist, our many shots are centered around a lot of maths that I believe are essential for our community to be exposed to. Tom, welcome to Geochemistry.
Thanks so much for having me, Sam.
So Tom, your path is not necessarily as important for our young listeners to hear about, since at one point you were a geophysicist, but I think focusing more on your role as a mathematical geologist in your journey through computers and data science and the geosciences as an evolving field is something that they could really benefit from. And also for our non-Aussie audience, if you could speak actual English, that would be a huge boon.
I make no promises on the English, but the other part I can probably have a go at answering. I think we're in like a really interesting time as like a science, as a discipline for geoscientists, because there are a lot of things that are changing right now. And I think there are a lot of these really interesting niches that people are going to fill, and they're going to be things like mathematical geoscientists, computational geoscientists, people who are able to leverage all this really interesting new technology and leverage all these really interesting new, ideas that I think are going to be really valuable to us as a community, as both explorationists and in the mine environment. So that's kind of always been the thing that I've been interested in, is like new technology has always really excited me, but I really like things where you can integrate good geological thinking with new technology. And the intersection of those two places is kind of the place I like to live.
And so at university, say, did you get a little bit into computers and more into math, or how did you really fall into this? Because it seems, even though a bit geophysicist, right? But, it seems like you go into the geosciences. How would you think that somebody, in university right now could get into more of a computational geologist or mathematical geology role?
Yeah, it's a really interesting question. My approach to geology was maybe a little bit different, where I did like geology, and I thought it was maybe potentially one of the things I might do before going to university. But the thing that became very apparent is like I wanted a job that I could work outside. It was basically one of the things. And so it turned up on like orientation day, and the person who was the head of school for geosciences is a very compelling speaker. And she was just basically made some really compelling arguments about like, here's some interesting things that you can do as a geoscientist. And I was like, oh, that sounds really interesting. Previously, I'd always been a bit of a maths and computing nerd. So it was kind of one of those things where I did both as majors, because I didn't necessarily know what I wanted to do until the very end. And then very luckily at Monash University here in Melbourne, Australia, there is some really good professors who actually straddle that boundary. So I got very lucky to run into them early in my career, and they kind of made it very apparent that you could have a career that was at the intersection of computational geoscience and really good geoscience at the same time.
That's pretty cool. I mean, my university experience was completely different. It was very, go figure, geochemistry, petrology heavy, definitely outdoors, but if we had wanted to do something mathematical, geoscience, I don't really see that back in, the day. That would have been something that I could have done, but something for everybody to be aware of now, especially now with everything being more heavy into the stats and the data science, as this is a field really that you could get into in geology.
Yeah, absolutely. And it's something that's I think going to be very interesting for us. And this isn't the topic for this podcast, but like in Australia, a lot of geoscience departments have been pretty badly decimated during COVID. We've lost a lot of knowledge and everything as well. So I think it'll be interesting to see what we as an industry do, because we might be having to go get people from other industries very soon, because I think we're going to be looking at a very different demographic of the people who were geosciences. I know from my experience in particular at university, the geoscience cohort was very close compared to every other cohort in the school, because we were the rock nerds. We did all geoscience together. We all did the same classes. There wasn't a lot of variability, so you were all going to do the exact same class. You saw everyone every single day in every different class that you had, and it'll be interesting to see what happens, because I think we might need people from different backgrounds and different disciplines to be coming in to not only become geoscientists, but also to be making sure that we are getting really nice and well-rounded scientists actually coming out of university as well, which I appreciate is not a topic for this podcast, but it is something I think is a little bit interesting, especially at the moment.
Yeah, and I didn't expect to speak so long on this topic, but I think it's just such a different conversation than I think that I'll have with any other guest. And I think it's really important for any of the, students or younger people listening to this that are interested in maybe an intersection of the two like you were, but now just being a completely different field really of its own, that it's just something that they should go into university, or even, halfway through, it's just something that they can think about, or even, go in, let's say they did geology and then, for their master's want to go do something more data science-y or mathy, then just knowing that maybe at Data Rock, there's a job for them.
Yes, that's true. Yeah, I'll do my best not to turn this into a sales pitch, but that's I guess a lot of the people that we kind of look for are people who are good geoscientists who either have an interest in this kind of thing or have a basic background in it, because ultimately, the best geological data scientist is a geologist, because the domain of geology is still so very hard to know and understand that it is very hard to get someone to go the other way. So if you look at a lot of companies who are trying to go from data scientist to geoscientist, that is a really hard transition, because you do forget actually how specific a lot of the knowledge is that you've learned as a geoscientist over the years. And we've definitely tried it teaching geology to data scientists, and it is a very, very hard thing to do.
Yeah, I bet. We probably need some more liquor to help out.
That's true. Yes, true. It's as with all geological disciplines, there's nothing that can't be solved by more alcohol.
Exactly. Yeah. All right, great. So this has been really interesting, and I think, not that I'm going to go back to university, but I think now, having had this conversation, I think it's something that if people have asked me about it, I could now maybe give some advice, but it's out there for everybody to have. For a guy so into math, for some reason, I just feel that you have some really great tea. So spill it.
So I'm going to go in a slightly different direction to how you might be thinking this is going, but I'm going to give you a bit of a prediction for what I think the world and for what us as explorationists are going to look like in the next 5 years. And I apologize, it's going to be a little bit long, but I'll get to my point here, which is, so my background is originally as a geophysicist, and thank you very much for offering an olive branch and letting me come on. But if you look at where a lot of our exploration success has been, particularly in Australia, but then as we move undercover and everything else as well, we've had a lot of success with geophysics, especially over the last kind of 10 to 15 years. There's been some really good, exploration stories which are rooted in geophysics. I think the next 10 or maybe 20 years is going to be a renaissance for geochemistry. And the reason that I think this is mildly gossip and mildly tea that needs to be spilled is because if you look at all the new technologies that are coming out, I think that geochemists are going to be so incredibly valuable that it is going to be an entirely different field, and it is going to be an amazing time to be a geochemist. So I'm really lucky that I get to look at a lot of new technologies that companies are trying out. And so my tea is, I think that geophysics is going to be taking a mild backseat to geochemistry over the next decade or two. So that's not just to make you feel good, Sam, but that is my projection, and that is me slightly falling on my sword as a geophysicist and saying there might be other things in this world than just flying airborne surveys. Geochemistry might be the way of the future.
Okay. All right. Yeah, it is a different direction for T, but
I know. I didn't want to gossip about you and me, Sam. I thought that otherwise it would be anything that you and I would have to say to each other might be a little bit blue for this. So I thought I'd go with something which is like slightly uplifting. And as a geophysicist, you can laugh at me later when I said geochemistry was great.
Yeah, I think I have to stop having, friends come on the show too, because there's always you just never know which way it's going to go with this kind of T segment. But this is a really good one, and I think that for the future people on the show, they should now think about having this sort of tea on there, because this is gossip of its own kind. I don't have many geophysicist listeners. I do have some friends that have congratulated me on the show, but maybe I'll just point them to this episode and be like, oh, it starts at about this time. You're too far into your career to listen to how Tom got his start, but maybe start over here. That's where the interview starts, and then they can see that and then panic, freak out, say this is rubbish, and
Absolutely.
Okay.
I presume I'll be kicked out of the geophysical union as soon as this comes out. I'll just receive my membership will be torn up into little tiny pieces.
Yeah, well, we do have, according to Spotify, I have 108 audience base, whatever that stat means. Okay. But I have about 350 listens so far, so I think that's enough to get your membership torn up. So great. Yeah, thank you for falling on that sword. And I think though that another thing that I've done this podcast for is because we don't have a lot of geochemists out there. And I think it's just, many companies, they're always looking for geophysicists. They have a much broader, bigger geophysics department. And there's only, most companies, even if they're very large, only have less than a handful of geochemists. And it's kind of like for somebody younger, how do I even get my start? Junior companies aren't hiring geochemists. Like I can't just go right into consulting because I don't, know how to do this in an exploration or mining setting. So where do I go from there? And so all the storytelling is trying to help people to get to these different journeys. But I mean, I think this could be cool if you're seeing all this and this is what your train of thought is going down. It could be something good for all those people that are just doing something that's very scientific right now to be like, ooh, there could be a spot for me in mining. Yeah, guys, please come hither.
Yeah, I think that's definitely the case. And I don't even say it tongue in cheek. I think there's some really interesting technologies that are coming out which are going to make geochemistry as we know it, I think is going to and this is not to say that geochemistry is backwards in any sense of the imagination, but the new technologies which are coming out, I think are just fascinating for what they mean. And I'm not an academic, but purely from like an exploration and mining standpoint, they are just absolutely fascinating. And I think it's going to change a lot of what we're going to do as an industry. And I think it is a very exciting time to be a geochemist, particularly if you're a geochemist who is in the early stages of your career. I think there's going to be some really interesting things which are going to come down the pipeline in the next decade, maybe even the next 3 or 4 years, which I think are going to make you incredibly valuable.
Yeah, and I would say one last thing before we move on, because it's kind of a weird thing to stall on, but I have the experience of working about 5 years for a service provider and actually in a business development role. And I think that seems kind of a strange place for a geochemist to end up for a little bit. But I would say that for anybody that's out there that's, looking to go down the path of becoming a geochemist for exploration or mining, I wound up there, at this point, mid-career, but my career will be going on where this will still be the beginning of my career probably. But I wound up there after having some jobs in exploration geochemistry, and to work for a vendor that is in new technologies is really rewarding. You get to be with a lot of people that are very senior in mining companies. You get to hear a lot of ideas. You get to grow in that sense. And then you get to learn a lot about new technologies and things that you wouldn't otherwise have that capability to learn in such an easy way. So it's something that I would recommend as an option for people to go and work in these types of jobs where you're working for vendors, because also it will change the way that you treat them going forward, which is important. Be nice to your vendors.
Yeah, no, it's a really good point, actually. And I think, and this is more like a bit of general career advice, like having a very broad base of experience, regardless of whether it's where it is, in terms of if you do everything from, as you say, from BD through to exploration work and everything else as well, the better feel you have for the industry, I think, writ large, the easier it becomes for you to find a place in it. Because it's often very easy for geologists to feel, I think when they're younger, to feel a bit pigeonholed. And going to say, well, this is where I have to live. I have to be an exploration geologist, and that's where I started, and that's where I'm going to finish. Where actually there's like a really wide array of options now, but there kind of always has been. But I think it's a good idea to make sure that you're getting exposed to these different types of opportunities, because, as you say, sitting on the other side of the fence every now and then is a good idea, because it can give you a much better feel for, I guess, how the industry actually ticks along and works, and it can help you identify opportunities earlier, I think, too.
Totally. And then you can also find somebody that, thinks you're cute and wants to teach you how to code. So, I mean, that's
exactly right.
These things happen. So then you grow your resume of things that you can do.
That's exactly right. That's the order of operations.
Speaking of, let's talk about the paper and your thoughts on the importance of spatial predictor variable selection, which I hadn't thought of or even known about until, a month ago, 2 months ago, and now it's all I can think about. So everybody that's listening, just sit back, get some popcorn, because this is going to be so exciting.
Exciting might be a strong word, but let's see what we can do.
We'll see what we can do. I mean, yeah, I guess, you get to a weird point in your life where you think it's exciting. I think for you, it's always been exciting, but yeah, I think people will get on the train. We'll have some people on the train, that's for sure.
There we go.
So when we were chatting about a topic of interest to you, I didn't give you too much leeway in things that I wanted to talk about. We kind of talked about like imputation a little bit, which was a weird thing that I wanted to talk about, a few years ago. And then we had kind of stumbled across this. And this paper actually was really well written. I could digest it, which is important for somebody that's not a maths person. And I guess really overall, it's got a pretty overwhelming title, but it's actually quite a simple and a very pertinent concept for exploration geochemists. Can you break down this title a little bit and then take us through why you selected this paper?
Absolutely. And maybe what I'll do is I'll say why I selected the paper, and then we'll work backwards. So the reason I selected the paper is because this topic is actually something that geochemists and geologists do really well, but machine learning algorithms do really poorly. And I'll provide you a little bit of an example of what we're actually talking about here. If we go and get, say, if we're looking at an exploration project, and let's say we've got like 5 or 6 different projects, and we had, say, soil geochemistry over all of them, what we want to know is if we have, say, one of these prospects, which is really good and really interesting to us, we want to know what we would look for in some of our other prospects that would make that interesting. And the way that we actually do that as a geochemist, like I'm one, I'm absolutely faking it. I am faking it here. But what you do is you think about geological process, and you think about the reasons why you might have anomalism, the reason you might have something that's enriched or depleted. A machine learning algorithm doesn't really see things in that way. What it sees is just data sets, and you can kind of think of it from a very high level as just columns of data. So what will happen is a machine learning algorithm will often learn something very stupid about your data. When we look at prospects as geologists, what we do is we go and say, well, I know there's going to be minute differences between all my different prospects, but I want to know what is the overarching theme of them. Can I kind of place these in context? And that is actually something that we do just great as geologists. And it's something we think about all the time. We go and say, what's actually important here? What is the subtle signature that I'm looking for that makes this good rather than what makes this bad? And machine learning algorithms are just horrible, just like absolutely horrible at this. And so this is a kind of an attempt to address that, to go and say, are there ways to build machine learning models which account for the fact that there is a spatial component of our data? And we kind of think about this naturally as geologists. We think about like how far apart something is. We think about, well, does that actually make sense for what I think the mobility of that element might be? We kind of naturally think in this way. And what we have to do is to build good machine learning models. We actually really need to have a way to teach our machine learning models this. And if we don't do it, we kind of get nonsense. And a lot of the nonsense that you would have ever seen, if you ever read a paper which has some machine learning component or even a statistical component, if you've gone and looked at it and thought, that doesn't look remotely reasonable to me, there's a good chance that the reasons for that are kind of some of the things that are being addressed in this paper. And that's why I chose this paper today.
That is exactly why I was excited that you chose the paper.
Yeah.
So in terms of breaking down the title, we're just basically, to sum it up for everybody in just one sentence, because you like to talk in run-ons.
Yes, sorry about that.
Yeah, so just in one sentence, why are we doing this paper? Just break down the title.
Exactly. So it's spatial predictive variables, which is, if I have two prospects, how do I find out if the variables that are important in one are important in predicting the location or some information about that second prospect?
Okay, great. I got that. No problem.
Yes, I and I'll try to keep my running on and waffling to a relative minimum. I'll do my best.
That said, I mean, your waffling does have its value. So maybe waffle a little bit. If I think you've gone on too far, I'll pull you back from it.
Yeah, absolutely. Just feel free to hang up on me. That's absolutely fine.
Before we move any further, it's essential that we define a few terms and how they're applicable to geochemical data. Random forest, similar models to it, say XGBoost. Can you just give us like a brief overview of what that would be?
Yeah, absolutely. And so from just very simply, all these are just versions of what's called a decision tree. And what a decision tree is taking some data, it doesn't matter whether it's categorical or numeric, and splitting that at some value. So one of the classic examples, and one that's a little bit morbid that's used in the data science world, is what information did we have about you on the Titanic that could tell us whether you lived or died? And it's a little bit dark, but it's a really easy explainer of this concept, which is, depending on what class you were in, depending on what end of the boat you're in, you have a really good idea about whether you lived or died on the Titanic. And that's what a supervised model is. It takes information to try to predict an outcome. The difference between a random forest and an XGBoost is kind of just like it's improvements on that technique. So we've gone from something that's very simple. So Leo Breiman had this idea of classification and regression trees, I guess all the way back to the 70s, but mainly in the 80s. And then the XGBoost, the light GBMs, the cat boosts, those are the modern interpretation of that, using all the advanced statistics and things that we know about sampling theory and all these things.
Yeah, and circling back to one of your original points, the machine learning model would do a really good job of telling us why somebody lived or died on the Titanic, but a geologist would do a really good job of why Jack died and Rose lived on the Titanic.
Correct, exactly right. Purely from of that thing. And these machine learning models are only ever as good as their data as well. So, and this is why often you'll get nonsense that comes out of them as well, because if you, and this is the idiom that people use a lot of, is garbage in, garbage out, right? If you don't have an entire context around these models, then you can't place them in context and do something useful with them.
Exactly. You did a really good job before, but just one last time, define for us spatial autocorrelation.
Yeah, so spatial autocorrelation is the idea that depending on what you do with a machine learning model, you might learn just the spatial location of your data. You might accidentally be not putting in, say, your easting, northing, and depth, but you might be accidentally representing a whole bunch of those things by how you present your data to your model. And that is why spatial autocorrelation is important, because you actually don't want to learn just really spatially local information. You want to learn broad scale information and see how that actually applies to other spatial areas.
Yeah, and I think for our listeners, I think a really good example of that is, if you're doing a stream sediment survey, and let's say that it's regional, but you're in this one area, maybe you're in Chile, you got some quebradas, you have some old streams, and it's just really easy to sample in this one area. So you've taken a bunch of samples, and let's just say that it comes back and your gold values are looking really good. And in another quadrant of your sample, you've only taken a few select samples, and those samples could be better in a way than those ones that came back from the same region. But because of spatial autocorrelation, the ones that are taken really close together just give you just an inherent bias in the data.
Exactly. And more to that, even on top of that one, the it kind of comes back to sampling theory as well. So as geoscientists, we'd love to go sample, say, once every 10 meters, exactly the same soil horizon or something as well. But that never happens. we have to be very specific where we take our samples, because mainly that's normally the only places we can take our samples. And so if we're not careful and thinking about like the spatial information about where those samples are and how we're forced to be biased in how we do our sample collection, we can get some really funny results.
Great. So looking back at the paper, the authors here are postulating that the characteristics of spatial data, especially spatially autocorrelated data, are widely ignored, and these results in models that can reproduce training data but are unable to make spatial predictions beyond the location of training samples. Can you just expand on that a little bit?
Yeah, and this is kind of again, this one actually plays quite nicely with, again, an example of how we do things now. If you think about how you might look at a geochemical data set, you can learn all these things about it. And let's use like a stream sediment example. You can go and look at it, you can go and say, this is what I think good looks like. But the thing that becomes interesting is if you go and collect out, say, a second stream sediment sample that might be from a slightly different catchment or a catchment that you think has some similarities, what you're going to try to do is you're going to try to apply that knowledge that you learned from one area to another. And with machine learning algorithms, the thing that becomes really important is it's not useful, or it's not always useful, just learning a whole bunch of information about a static data set. What you care about is how can I apply that information to go learn something about a new area? And often that concept is just entirely forgotten about in how people build machine learning models. And the reason that this becomes important is if you don't account for it, you're just going to produce slight nonsense. In saying that, there is actually another kind of sister paper to this, which says essentially spatial autocorrelation. Actually, no, I'm going to stop there. I'm going to look up the name of this paper, Samantha. Yes. Okay. So there's a paper which is called Spatial Cross-Validation is Not the Right Way to Evaluate Map Accuracy. So there's actually a paper which postulates the exact opposite to this, the things that we're talking about. And that paper is actually really interesting because what it says is depending on what you're trying to do, the spatial autocorrelation doesn't necessarily matter as much. And the reason that they postulate that is because they say, if you're not predicting outside of your spatial area, if you're not going to, if you're never going to go collect more data, if you have a global database and your space is never really going to change, then this approach doesn't really matter. And so that's why this is kind of both important and not as important. It's because ultimately what you want to do is you want to go and say, what am I actually trying to achieve? And what you're trying to achieve is, I'm going to build a machine learning model that I'm going to apply to new data. And that's often what we do. But the reason I actually quite like the paper, which says the exact opposite of this, is because that paper points out that that's actually true in some cases, but not all cases. And that's why that's really interesting, is because this is a problem which relates specifically to learning something from one area and transferring that information to another spatial location. If you don't have that problem, then actually this spatial autocorrelation just isn't something that you're ever going to really need to come across.
My mind is just brimming with 1,000 questions, and I'm going to make the absolute worst analogy here. But Please. Maybe I'm just going to go with it. You're familiar enough with Chilean geology. Listeners, I worked in Chile for a long time, and I'm from North America, but my mind just goes into Chile mode all the time. So let's say that you're in the El Indio Belt and you got some stream sediments, regional stream sediments. But then let's say that your company decides that you want to, besides just working in Chile, they also want to step out a bit into Argentina, and they want to step out a bit and they want to work into the Maricunga Belt. So you're saying in that case, spatial autocorrelation is super important because now you're doing these step outs. But let's say that you're working in the El Indio Belt, and your company's like, actually, we just really want to chase up some anomalies over here or over here. And for that reason, the opposite is true.
Yeah, and to a certain extent, if you're doing, say, infill sampling, you're kind of doing a little bit to address spatial autocorrelation already. You're actually going to do that. And so the reason I do like that paper, which says the opposite, is for exactly that reason, where it goes and says, this is really important depending on how you think about it. But equally, you have to, and this is a good bit of life advice, is trying to do good science is a good idea. And so if you think about how your data is going to be used, you'll always come out with a better result than if you just go and say, spatial autocorrelation is the most important thing, or spatial autocorrelation doesn't matter. both those things are equally true. Both those things are equally wrong, depending on actually what you plan on doing with your data.
Just for the geochemists out there and the budding geochemists, I guess what I would say to that is perhaps if you're looking at doing some machine learning applications, something that you should do before and during planning your survey this day and age is, besides getting all the geochemical and geological things correct, that you know to be correct, checking your drainage basins, for example. You also, if you don't know a lot about data science yourself, you also would want to consult with somebody. A lot of companies now have data scientists, and you probably went to school with a data scientist at this point. So you would want to at least consult with somebody that knows a bit more about these things before, making your final sample plan.
Exactly, and this is actually something that you'll often just think about anyway. Like it'll be naturally the thing that's kind of scratching at the back of your brain, where you sit there going, we don't have many samples for that area. And actually, is that just some local anomalism which doesn't relate to anything that I'm interested in? And is that just like a tellurium anomaly, which actually has something to do entirely unrelated to the process that I think it is? And you kind of already have a feel for this, but it's interesting because it does come up in like the data science world. But even if you start doing things like principal component analysis, linear discriminant analysis, which are like things that are on the data science path, even those kind of things can be affected by this, because they are things that are affected by sample population. These are things that are affected by data populations, and so it can actually be something that you might accidentally run into even if you don't realize it. Because the idea of this spatial autocorrelation, in this paper they talk about like fairly high level machine learning models, but you actually can run into this anywhere, and it's a matter of how can we help identify when we might be running into it, and how can we hopefully try to address it.
Yeah, and I think that's something that I probably had a few questions down, but we might as well just talk about right now, those two questions, because I think for us to not address them here right now would just be irresponsible to our listeners.
And we can't have that, Sam.
We can't have that. That's not what I'm here for. And that's not what you're here for. So
well, maybe.
Please,
we'll find out.
Go on.
I'm happy to lead everyone down the garden path as far as we want, Sam. So you let me know.
I think let's go down the garden path of these. I've never said that phrase before, so thank you. But let's go down the path of those two questions, because I think to be able to get to a place where people can start to be thinking about this and answering those themselves is going to be important.
Yeah, and so one of the classic examples that we teach as a company and like how to think about this kind of stuff is, let's imagine you had a data set which is it's spatially biased towards the north of a deposit and the south of a deposit. And let's say what you do is you say, well, I think there's something in here in terms of like, I think I can see some vectoring indicators. I think I can see some mobile elements which are moving away from my deposits to the south of it. And what you'll do is, if you built a machine learning model, it doesn't really matter what it is. It doesn't really matter if you just come up with a set of rules of thumb that you go and do, where you go and say X greater than 50 ppm is important. What's important is not that rule works there. It's how applicable is that rule elsewhere. So if we come up with a rule in the southern part of our deposit, does it work in the northern part of our deposit? If we come up with a rule in the northern part of our deposit, does it work in the southern part of our deposit? Is there a rule that actually unites the two of them? And so that is kind of the basic question that we postulate to new starters for us. But that is kind of the crux of the thing that we're getting to here, which it goes and says, we actually have two examples of like some drill holes, which are X amount of distance away from the deposit. Can one that's in one geological spatial location predict another? And you can kind of think of it as like, that's the crux of this entire thing, which is, if you can answer that question to go and say, yes, these two can predict each other, then that becomes really useful. But if they can't, that's actually super useful information as well, because that might tell you that there's more complicated ways that you need to integrate these two different data sets. And that's kind of, from a very high level, the conceptual way that I think about it is, can we actually use one area to predict another? And if we can't, what does that tell us about this process? And that is, of course, where your machine learning modeling has to stop, because a machine learning model can't tell you why something went horribly wrong. That's when you've got to stick your geologist hat back on and go and say, okay, the reason for this is XYZ. It's because we're in the hanging wall now, we're not in the footwall. It's because we've actually crossed an unconformity. It's because actually the way that the permeability was in the northern half of our deposit, it meant that actually we see entirely different things 300, 400, 500 meters away from our deposit, rather than in the southern part where we had different permeability in our rocks and therefore things look entirely different. So that is my short, but not overly short because I have a tendency to waffle, idea of how you think about these things.
Yeah. Oh, I'm really digging in here. I think it's a really good one just because something that they point out in the paper is that if you have these spatial temporal dependencies that can cause a misinterpretation of certain predictor values, making your algorithms fail, predicting beyond the location of the training data, these are things that we have to know because from back in the day when I thought about machine learning and, everybody's kind of, when they don't know so much about it, they just get very upset about black box nature of things. And they just say black box, black box, black box. But I think that out of everything, this is something that I never really thought of in terms of that it could come down to X, Y, Z. And that literally X, Y, and Z, depth, north, south, right? And for that to be a huge part of your problem, it just makes you rethink everything in terms of being a geochemist. Because now you don't just have, okay, well, gold isn't correlating with arsenic, so what's going on? This isn't maybe an arsenium pyrite gold situation. Okay, move on, next thing. But start talking about these things, and it just, you have me questioning myself for a few days there.
And I think the point that you make there is actually a really nice one, because it's kind of one of those things where I think actually machine learning practitioners have done themselves a disservice by trying to think that this is like some magic that you shouldn't engage people in the process in. But I think also this is like the classic example of where you start with one way that you think about things. And this is like the same from my career as both a geologist and a geophysicist, where I was like, okay, I understand something on some level. And then you dig into it a little bit. And then you go and say, oh, actually, maybe I don't understand that as well as I thought I did. And then you dig into it a little bit further. And then you go, well, actually, I understand this even less than I thought I did. And you kind of keep digging down and you keep learning about these things. And by the time you get to the end of it, you're like, I don't think I know anything. Like there's so many interesting, complicated questions and all these things as well. And this is one of the ones that machine learning has. It's one of those questions where you kind of sit there occasionally and you go, this is a really hard problem to solve. And there's no one way to solve it. But this is actually something that and this is the reason I quite like this concept, is because it's one of those things where if you start your journey on machine learning, eventually you'll run into this. And the moment you run into this will tell you a lot about how you feel as a person to learn something that you might have been wrong about. And like, I know when I ran into this, it was like a light bulb going on, because I was like, this is so obvious now. But before I kind of stumbled onto this concept, I was like, it wouldn't have occurred to me that this was a problem. But when like this paper, and there's a bunch of other ones from Maya and her group, which are really good on this topic, I read those papers now. I'm like, I give this paper to people who are doing machine learning models, because this, I think, is a really good example of a high level look at some of these concepts, which can just absolutely like make your models just absolute nonsense if you don't think about them.
Yeah, and I think it's just so relevant for our industry, because we are all about space matters. It's what we do.
Yeah, so. Exactly right. And the spatial component of everything is just so important. And we think about it naturally because we look at data spatially. Machine learning models are just like, give me some data, I'll give you an answer. And that's what we need to be careful with. And we have to kind of, ironically, we have to trick these models sometimes in certain ways into thinking about the spatial component without biasing it too much. Because the biggest danger with all machine learning models is we start putting our finger on the scale to try to solve one problem, and all we do is we introduce another one. And that's a big problem.
I think it's such an important one just for anybody that's listening to this to be talking with, whether it's data scientists in-house or it's a provider, or if they're doing it themselves. But it's something that, again, maybe I'm just so out of the loop that, everybody talks about it and I just didn't know about it before. But I mean, it's just something that's so important for all of us to be aware of. And if we get back this model that seems to be doing such a great job, but in the end, it's not taking this into account, and it really needs to be, not that it's scary, but it's scary in the way that you shouldn't be putting a $500,000 drill hole over there, drilling down 2 kilometers to find a nice bunch of ore, because actually the whole model meant nothing.
Exactly. And you've hit the nail on the head there, right? Where it's part of it's a de-risking thing, because you actually, if you're going to go make a decision, you want to have as much confidence in this data as possible. And then part of it, as you say, is how do I make sure that this is telling me something useful? And how do I make sure I'm getting the most out of my data? Because that's all really machine learning is in a lot of this context. It's how do I get the most out of the data that I already have? And that's the kind of things that we try to address, and that I'm quite very clearly, by my waffling, very passionate about.
Yes. And we have waffled about this so much.
Yeah.
And each time I will say I've learned something new. Switching gears a little bit, I wanted to talk about recursive feature elimination. It's fairly straightforward. The variables that are most important for your model will have the highest Gini score. The furthest to the right a feature is, for example, an element or a mineral, the more important it is to a model. Typically, you take the features that have the highest importance and use that in the next iteration of your model. So now you have the authors here arguing that the backward recursive feature selection fails to address the issue of overfitting, and furthermore, if a variable leads to considerable overfitting, it's highly significant in the models, and the recursive feature elimination process will keep those features as important and not remove them, even if it results in high spatial error. I mean, in the context of the paper, I think it's more important to talk about this because it's just too broad to just jump into as a whole. But what's your opinion on this statement? Because it kind of blew my mind.
Yeah, no, it's a really good, it actually is a good statement that I quite like, because essentially what it's saying is that recursive feature elimination, which is the idea of you throw all your variables into a machine learning model and you sequentially remove them one by one. And what you do is you take whichever one had the least overall effect on the model, you remove until you've only got one, and then you can build this recursive feature elimination curve. It's a really good technique, but you can imagine that if you had, say, a really high spatial concentration of data, so let's say you went and just sampled, I don't know, the same 1 by 1 meter square of sand again and again and again and again for sediment sampling, and you just kept on sampling that, and then you said, that's good. This square of ground is good. Everything else is bad. Your machine learning model is going to learn everything so hyper-specific about that 1 meter that actually this recursive feature elimination, which is normally a really effective tool, is going to learn complete and utter nonsense. And this is the crux of this paper, which goes and says, if you go and just look at that, that's not applicable anywhere else. That's applicable exactly in your 1 meter sand pit. But if you go and say, I want to go look at a different sand pit a kilometer away, do you know anything about that? Or actually, in reality, is all you've learned is something so hyper-specific and it's so overfit. And overfitting is the idea of like a machine learning model which knows both the signal of what you're looking for, but also some kind of local noise or something. Just it knows both of those things intrinsically. So it could only ever be used on if you found that exact same 1 meter by 1 meter sand pit somewhere else. And as soon as you find even a remote variant on that, it's not going to work. And so I think it's something that's a really good, useful thing, because what you'll do often is you'll go and find these really accidentally, you'll just learn something really local, and then that local information just doesn't transfer anywhere. And that's like a big problem, obviously, because if you learn information about one area, you can go down and do all these really detailed analyses, but how do you apply that somewhere else? And kind of the underlying answer is, and the point of this topic, I guess, is that maybe you can't. And so we have to think about ways to try to avoid that.
Yeah, I think that's a really good point. And I think about that when I used to do a lot of these with you, actually. And we would, at first that concept of overfitting was very difficult for me to understand, because I was like, oh my God, but look, the model, it's working perfectly. That's what we want.
Absolutely.
But yeah, the whole thing about it being specific but general enough where it can continue to learn. And I think you did a really good job of explaining that with the author used something else, but the 1 by 1 meter by 1 meter by 1 meter sandbox, that's top notch.
I'm a simple man, so when I think about things, I've got to think about like me digging in a sand pit. That's the only way that I can think of, of actually ways to do things.
Right. Moving on, So according to the authors, spatial variable selection essential for automatically removing variables counterproductive to spatial mapping to provide scientifically valuable results. But sounds like the authors here are suggesting that we plan our geochemical surveys in a different manner than perhaps many are used to.
Yeah, and I guess there's like one underlying thing which underpins that statement in this work, which makes it unfortunately non-transferable to other work, is a lot of time we just can't. Like you'd love to sample evenly when you go out and do a soil sample. And geophysical surveys, again, you sometimes get this for free because it'll be an airborne survey. But with geochemical surveys, often you can't do this. And so the reason this is actually quite useful, and the reason I do like that statement also, is because if you go and just find out what the important variables are in all your different spatial locations, if they're all different, that's actually super useful information. But what it does tell you is that you might have different local influences, but what you have to do is you have to go find out what do they share in common and what do they do there? Or do you actually have to go build 40 different machine learning models? Because instead of you going to say, I think that this is, for example, and let's use, say, porphyry signatures as an example, you could go and build a model for each individual porphyry model, and all of them would be wrong because each porphyry has something slightly different about it. Or you could use the classic porphyry model, and equally, it will be wrong no matter where you go because it's actually too broad and too general, and each porphyry has something like slightly that means that it's eroded part of this zone, so we don't see the advanced argillic zone or something. And so basically the reason that statement is kind of useful and also useless for us is because often we don't get to choose where we sample. We kind of have to, we are the poor cousins of a lot of these things where we can't say we can't go and sample every 50 meters. We just go and we take a sample where we're able to.
Yeah, and back to the Chile example. Yeah, you can get dropped off on mountain cliffs sometimes, but can you then sample in a gulch? I mean, not always, right? So if you're just going, 50 by 50, or that's pretty expensive sampling there. But if you're just going,
great, yeah.
Yeah, it would be great. But if you're just going kind of those regular boundaries, anyway, it's really going to be pretty hard in our industry because it's not something that's as easy maybe as the sampling that she was trying to do.
No, exactly right. And that's just literally the classic problem that we face, is that we try to solve for spatial autocorrelation, also knowing that half the time we can't do anything about it because we just drill a lot of holes in one area, or we go and sample in one area because it was interesting, or because that's the only place we could do it.
Mm-hmm. Good point. So then there was also a large discussion on predictor variables in addition to our typical data elements, for example, or minerals. And the authors were obviously discussing spatial variables. But for me, it got a little complicated in terms of cross-validation. So the suggestions were for using a random and a spatial cross-validation in the different iterations of the model. They wanted to use recursive feature elimination to improve the model, even though previously they had stated that they didn't want to overfit the model this way. And then to make it even heavier for me, they threw in k-folds and data splitting. Can you just break down what happened here? Because I'm still not sure.
Just to make your life difficult. Yeah. So
please.
The way that we typically might build a machine learning model is we'll train on, say, 66% of the data and we'll predict onto 33% of the data. And that's great. And that's actually fine in most normal circumstances. And that's the idea of training on something, testing on something else. And you might grab that 33% randomly. And that's kind of the idea of taking some random samples out of it. But the thing, again, the answer that we actually want to know is we want to go and say, well, what if we just split our data halfway? So let's assume we've got a soil sampling campaign that's, say, 100 kilometers, roughly, give or take, so from north to south. What if we just drew a line halfway through the middle and did recursive feature elimination and all these things on both of those areas? And instead of saying, how well does my model work on the random 33% that I held out, what we can do is we can go and say, how well does our model work on the north predicting the south and the south predicting the north? We actually probably want to even go even more detailed in our case, because we actually might have different, maybe basins. We might have different catchment areas. We might have different geology. So maybe what you want to do is you want to actually break all your data up into K folds. So in this case, K is just any number. Folds is like a set of different groups. You might want to break your data into those different groups and then hold each of those groups out and then test onto them and then see whether you're actually able to predict them. And so this is kind of the idea of, you can start with something very simple. You can do just like n cross-fold validation. So you can break your data into 10 random groups and then just go and test and train on all those 10 groups. But maybe you actually want to be specific with how you choose those groups. Maybe you want to choose them by geological domain, by catchment, by even just turning them into this idea of block cross-fold validation, so block CV, which is you'll just break your data up into maybe 10 different spatial boxes and then just hold those out. And instead of holding stuff out that's random, you'll hold out stuff that actually has some kind of coherence to each other. And you can use recursive feature elimination, something else as well. And maybe a nice example of this is an analogy to keep us actually back on the geochemistry track, which is we did this once directly over a deposit. And what happened was you found that iron and sulfur were really important over one part of the deposit, and it wasn't important anywhere else. And so for me, when I saw that, I was like, well, to me, and based on what I kind of understood the mineralogy of the deposit, it looked like there was probably pyrite alteration, or there was a lot of pyrite in that particular part of the deposit. And that's 100% what that was. But they had a lot of samples from there, and they didn't have pyrite alteration anywhere else in their deposit, or they didn't really have that much pyrite alteration. So the thing that was really important was for us to know, if we go and build a model off a sample, which is incredibly biased towards all of these samples where we have iron and sulfur being important, that's the only thing the model's ever going to learn. It's not going to learn any of the other subtle signatures. It's only going to learn that signature, which we think is dominated mineralogically by pyrite. And as soon as we found that out, it became very apparent that we had to be very concerned about spatial autocorrelation in that particular project.
Just took a few minutes there to really appreciate that example. And I think it was a really good one. And I think it really illustrated a lot of the different points that I had questions about. So maybe we should just tell these authors, for our sakes, just to always include a geology example when they're doing things.
Absolutely. I have a very much like an academic crush on this particular author, because she just writes very good, accessible papers. And I think that's just such a valuable skill, to write good papers that are super accessible and can get across broad concepts. I think that's just like such an amazing skill that not a lot of people have. So I won't be saying anything to these authors, Sam, because I think they're perfect.
So I'll leave that there, but then I'll also say, in addition to that, for anybody listening to this, it sounds like perhaps, I don't know, that I know a lot about this stuff, which is true, but also I don't, in the sense that reading a paper like this is normally a very difficult thing for me to do. That involves me falling asleep a lot, because number one, not my cup of tea, but number two, also they're just so dense that it's very hard to get through them, get through the math. And if you have any level of background in stats, machine learning, you can read this paper. So my background, I would say, is maybe along the order of maybe 10%. And I got through this paper, I understood it. And it was, I'm not going to say quite that I have a crush on this author as well, because I think that's premature. And I reserve my crushes for people that are very deserving. But I'm on the way. I'm on my way, because this was some very complex concepts that she boiled down into things that actually somebody with 10%, maybe a little bit more, understanding digest.
Yeah, exactly right. And I think that's, it just makes this much more of an accessible topic. And I think that's just fantastic.
Yeah, especially considering that we're talking about geochemistry, where we are riddled with said problem.
We are. It is absolutely an issue, and we need to think about it. Yeah, I could not agree with you anymore, Sam.
Everybody go and read this paper.
Absolutely.
Forward feature selection versus recurse feature elimination. Thoughts, recommendations, go.
Yeah, good question. Very open. There's probably a very boring podcast we had just on the difference between these two, Sam.
Wow. Okay.
Yeah. So I won't go into this one. I will intentionally be very brief on this one, just because it's not super interesting, and it is very situation dependent. Recursive feature elimination or forward feature selection both two different kind of sides of the same coin. One of them, what you do is you start with one variable and you add whatever variable improves your model the most. The other one, you do the opposite. We start with everything and then you remove them recursively. Generally, and I can't necessarily think of the reason for why this is, and maybe there's a very obvious reason, and I don't know whether you get fan mail, Sam, but if someone wants to write in and tell me why this is, this would be great. Recursive feature elimination is the method that people use a lot more. And the reason I think that is because it's a little bit easier to set up in terms of if you're writing a piece of code out to go do that, it becomes very easy. And that's kind of the method that I use and that I prefer. But I'd be inclined to do both, because ultimately there's not really a massive computational penalty for doing both, or doing things like looking at shack values or looking at something else. All of these things, it's just a matter of making sure that you're using whatever is the best method for the question that you're trying to answer.
And I'll have everybody know that I don't receive fan mail. I get fan email. And you can email us at info@geochemistry.com.
Fantastic. I'm glad.
Or go to the website and just go to the little comments. I don't receive mail. Come on.
That's great. No, I'm glad that I'm glad that we could get a good plug in to the email, though. This has been worth it.
Yeah, exactly. So I have a few more questions, and we're just going to go through them because at this point, I think that anybody that's still listening is very involved in what's going on and what's happening.
Right.
So let's say that we're interpreting a stream survey. We're not inputting the location as a variable.
Yeah.
And in this sense, how come it's important in the outcome? When we are doing any kind of thing, we're not being like, okay, and the coordinate is this and that. But this paper and this whole concept is saying that that's still really important, even though it's not even in there.
Yeah. And maybe the easiest way to think of it is, let's say you had two ends of a stream sediment sampling. You'd collected some data in the south, some data in the north, and you were going to do clustering. And all clustering is grouping data into the things that are similar. Ultimately, if you think about let's say this is a perfectly stream which runs exactly north-south. If you had a bunch of data which is going to have a y coordinate which is going to be high, and a bunch of data which is going to have a y coordinate that is low, and all the other data has like a bit of variability in it, the thing that your clusters are going to learn are just like one data was in one location, one data was in the other. And that is obviously just not useful information for us to learn. We want to learn subtle signatures and subtle things. And if you put the spatial variables in, you're normally just going to see your clusters spit back out at you as spatial, as the things that are the dominant feature of your cluster. And that isn't always useful. And so that's something that really is the reason that that I personally don't, in a lot of the work that we do, we're very unlikely to put spatial data in as a predictor or as an input variable.
No, agree, because thinking like it's important, but at the same time, we're not telling it what the spatial coordinates are. I was thinking about clustering as well. It's very intriguing that it's a variable that we don't technically use, but it's very important towards the outcome.
Absolutely. Yeah. And it's one of those things where you can, and this is concept of like data leakage, which is like you might accidentally give a machine learning model some information that you didn't mean to. And you can often do that with spatial data.
The more you know.
That's it.
Another term that I hadn't really heard of much before, but it's spatial variable selection. Authors are saying that it's required to remove misleading variables from models. How do we do this?
Yeah, and if we go back to the example of the deposit that we worked on, where you had iron and sulfur as being really important in one part of the deposit to tell when you were like spatially close to the deposit, but you weren't exactly on top of it, that is basically where we go and say we have to, as geologists, put our finger on the scale and do something to our machine learning model. And so what we can do is, in that case, because of the way that we understood that system, we removed iron and sulfur. So we basically just said we're removing iron and sulfur from that. And we also removed some correlated variables in there as well, because what happened is iron and sulfur, and I'm hopefully not telling anyone anything they don't already know, but you often see things which are really highly correlated with iron and sulfur in geochemistry. And so We had to remove a few other variables as well. I think tungsten, and there was a few others I can't remember off the top of my head, but that was actually really important, and that gave a much better general model. And that general model, and this was a concept you and I just briefly touched on before, meant that there was a lot more applicability to go do other things with this data.
For sure.
Where previously we couldn't really do that.
This is also counterintuitive to the normal workflow of a geochemist. So it's nice to be hearing something that's machine learning versus what we would normally do, which is looking at iron and sulfur. We're thinking, we're doing it mostly to see what our pyrite line is. We're thinking about elements that could be related to pyrite in the system. So the way that we'll do exploratory data analysis, it's still very correct, listeners, team, to be using all these information. But when doing some kind of machine learning, this is where we need to start considering these other concepts, some of which we're touching on here. Last question that I have for you, we've come to it, is that, so I found a really interesting outcome of the study is that they conclude that the models that they were running performed equally well, statistically speaking. However, when doing a visual assessment of their data results, they found that this didn't necessarily hold true. So I think something that we see the opposite of in, say, a stream sediment survey, where you can have an area that looks really good. So like think about all those gold, good high values clustered in one area, except that it's caused by having said grains that contain gold in that area, and not as good as some others. So when we're looking at our data, we see things that look really good, and we're like, okay, definitely we got to search in this space, but this whole principles and these principles that we've been talking about at the same time, it's just exactly the opposite of what this paper is really saying.
Yeah, and I think it's both, and this is kind of the reason I chose this paper, is because it's actually something that we're quite good at doing this, because we think about process when we're looking at these things. Because you might look at something and go and say, well, the gold's enriched in one particular area, but you'll go and look at it and you don't just say, well, hopefully, we don't just say the gold's enriched in that area, therefore that area is the most prospective. I'm going to start just throwing drill holes at everywhere that's on either side of that gold anomalism. In saying that, sometimes we do that, and that's not a great idea. But hopefully, we can do smarter things than that. And this is, and the visual assessment is always a good one, right? Because the proof is in the pudding. Because just because you get a machine learning result which has a great like performance, it has a great F1 score, that doesn't actually mean that it's useful. And it's not until we actually put it back in spatial context and we go think about what it means. And then we go and decide what is the decision that we're going to make in terms of, are we going to go do more stream sediment sampling? Are we going to use some kind of model? Are we going to come up with a basic set of rules to go do something? All of those things are things that we do intrinsically in our mind. And these are things which are actually very hard for a computer to do without us providing them the right information. So this, ironically, talks exactly to the point that you're making, which is, often all these machine learning models, they can be a black box, they can be an opaque box, they can be something which is just very simple statistically. The thing that'll really matter is what you choose to do with it afterwards. And that's kind of the underlying thing here. And that's, I think, a really good example, the stream sediments example as well, where you need to make sure that, is this setting anything off in the back of your brain saying that makes no geological sense at all? And that's ultimately what we try to do as exploration geos, and that's ultimately what we're trying to do with any of our data sets, is we're trying to figure out, can I trust my conclusion? Have I de-risked my conclusion? What is my next move?
Yeah, and really very elegantly said, John. I mean, just wow. Thing that I just wanted to add for everybody, and it's kind of a little bit off topic, but it's just the fact that, and I think, Tom, in your own words, this would probably go over much better. But if somebody asked you, say, to do an equitip study on their core because they were looking for hardness throughout their deposit, let's say that you're starting with 10,000 meters, but then next thing you know that they have a few thousand meters more here, 1,000 meters more there. With machine learning models, would you recommend that what the original model that they generated, that they just use that every time? Or is there this whole thing where it's really important that you need to always be calibrating your models and always be, keeping things up to date as it learns more information?
Yeah.
Is it AI?
Is it AI? Yeah. Unfortunately, no. Most geological machine learning models aren't sentient yet, which is probably for the best. But you kind of always need to be testing these models and making sure that they're working. So much like when you're logging a deposit, if you logged it the same way that you logged it after you saw only the first hole that went into a deposit, you'd probably log it fairly poorly. You'd have some information, but you wouldn't have the whole picture. That's the way you can kind of think of a machine learning model. It will be useful, it will be good, it will be general. But if you went and, say, drilled a step-out hole where you go and drill outside of your deposit on the other side of a fault, and a couple of 100 million years have passed in terms of the age of the rock on either side of that fault, expecting that model to work is probably a little bit ambitious. And so ultimately what you should do is you should always be, at some way, much in the same way that you do, I guess, referee samples for geochemistry, the things that you do repeats for geophysics, all that kind of stuff. You should take the same approach to machine learning, where you should always be QCing, you should always be updating, and you should also always be aware of the situations where maybe it doesn't work well.
I'm going to have a think about everything here that was said today, and probably catch up with you later this week to go over at least half of what you said. Thanks so much for being here, Tom, and I hope that everyone out there listening got as much out of listening to this as I did. And honestly, great recommendation for that paper. So thank you all for listening to Geochemistry, and a big thanks to Tom Carmichael for stopping by the show, dishing some tea, and taking us on this math journey. Thanks to our sponsor, LKI Consulting, and to It's Water and Coma Media for our music. And I'm looking forward to chatting with you all next month when we talk about chromium, PGEs, and crystal mushes with Jason Cummins.